Hi, welcome back. So far we have covered the concepts of the concept of current and defined charge and flow of charges and so on. Today I'm going to focus on electric potential and voltages. But before doing that, just a quick warning. Okay, so far we had that in our equations, our currents could be positive or negative, and that the reason for that is that when we define this function q of t, Q of t was the flow of charges through a certain cross section, and it was associated to a direction, right? We said, let's say Q of t, this function Q of t gives the flow of charges to the right in a given cross section. With that choice, then the currents and delta Q could be positive or negative. And that was just telling us about in what direction the charges were moving. By the way, from now on, when I talk about motion of charges, I'm talking just about the motion of the positive fictitious charges. Okay, so if you define as a q of t like we did in class, in the examples we did in class, a q of t as being the flow of charges to the right in a certain cross section, and you get a negative I, that just tells you that the charges are actually moving to the left in your surface. So negative current in one direction, well, say you say the current through this section to the right is negative, just tells you that actually the current is positive to the left, so that charges are moving to the left. Now, what we're going to do from now on, so it gets a bit confusing, right? So from now on, if we focus on the following definition, we say, okay, we just pick the direction of the motion of the positive charges as being the direction of the current. Then with that choice, all our currents will be positive. They will always be positive. So you indicate the direction of a current in a wire, you specify the direction of the motion of positive charges. With that choice, all I's are positive, and we'll stick to that for quite a while. Okay, so all the equations in the equations I is positive. Okay, now we can address the meaning of voltage and electric potential. Ohm's law, recall from high school, is this. Now, actually, you probably have learned it in a different form. You probably saw something like this: V equal I times R, or V equal Ri. Actually, a better notation, for a reason that will become clear in a second, is to use a delta V instead of a V, because here, you see why in a minute. So it's really delta V, and to be exact, because delta V can be positive or negative, to be exact, we should put absolute values. So this is really the better way of writing the equation, the most clear and precise. You'll see why shortly. So what's the meaning of delta V? What does it represent? So delta V, well, from the notation here, delta V, you can expect that this will be a difference of V between 2 points. Now, just a warning, obviously we use V here. V will not stand for speed. So this V is not the speed. And delta V is a difference of V's between 2 points. So the question is, what is this V? We'll define that in a second. Now the units of this V and delta V are volts, named after Alessandro Volta, who also lived towards the end of the 18th century, early 19th century, as the other scientists we mentioned before. So what does delta V mean? Okay, just a quick reminder about mechanics, potential energy mechanics. Well, energies are measured in joules, named after James Prescott Joule. And remember, in mechanics, you talked about several forms of potential energy. One is gravitational potential energy, mgy. Now, you might have used mgh, but mgy is a better notation, because h is only, you might think that h is always positive. Actually, it's really y we use here, and this y can be positive or negative. So UG, I use U for potential energy, so this is gravitational potential energy. U sub G might be positive or negative, depending on whether y is positive or negative. Just one quick comment. You see from this equation here that UG is a product of a property that depends on the particle times something that depends on the position of the particle only. And we'll see a structure like that again in the context of electricity. Now, when you define U sub G, uh, is equal to mgy, the value that you get for this depends on the value of y, and the value of y depends on where you put your origin. So it's clear, you have a building, let's say you have a baseball here that you drop from the top of the building. What's the value of the gravitational potential energy of that baseball? Use mgy. Now, someone could say, okay, so mgy, what is y? Y is measured with respect to a coordinate system. I could put my coordinate system right here with the origin here. With that choice, y at that point is 0. So the baseball here has a gravitational potential energy equal to 0. Okay, but you can put also your origin here. If you do that, then when the baseball is here, y is equal to h, the height of the building, and you get mgh for the potential energy of the particle. Now, there's nothing that prevents you from putting your origin here or anywhere you want. So everybody can have a different value for mgy, depends on their choice of origin. But in the end, it does not matter, because when you calculate something physical, like let's say I drop the baseball and ask you, I give you the initial speed, and let's say I drop it from rest and ask you how fast is it moving on the ground when it hits the ground. It turns out that when you calculate that, everybody will get the same answer no matter where they put the origin, because it's only the difference of potential energy. I should have said energy here. It's only the difference of potential energy, mgyf minus yi, that enters the calculation of, let's say, the final speed here. So it's always the difference here that enters the calculation of anything that you can measure, like a speed. And this value, this thing here, turns out that this result here will be the same for everybody, no matter where they put their origin. In the end, you always get you'll get a different value for the initial potential energy and the different value for the final one, but the difference will be the same for everybody, no matter where they put the origin. We'll see something very similar in the context of electricity in a minute. Okay, now let's go back to voltages and all that. First, a question of terminology. There's a big difference between what we call the electric potential and the voltage. Now, okay, the notation here gets a bit confusing. First of all, be very careful. I'm talking here about the electric potential. There's also something called the electric potential energy that we'll define later, which is very different. Okay, they're connected, but they're different things. So it's very important when you talk about the potential here, whether you talk about electric potential energy or just the electric potential, they're different. The other thing is that electric here, I'm going to drop often the word electric, because I'm focusing just on electric circuits. I might talk just about the potential or the potential energy, but I must make the distinction between potential and potential energy. Now, electric potential, in everyday life, people usually don't use that word very often. We talk often about voltages. So I'll tell you how they're related, but they're different. Okay? So we use the symbol V to represent the electric potential at any given point in a circuit. Okay, now just a warning, it's confusing. V in an equation usually means the electric potential, but we use also V for the units, right? If you write, let's say, a battery, you say it's a 12-volt battery, you'll write 12 capital V. So sometimes we use capital V to represent the unit, when you write a number and write the units after the number, or we use V to represent the electric potential in an equation, and they're different. So it's confusing at first, but it'll be, when we do some examples, you'll get used to that, okay? But at first, it might be a bit confusing. But now it's electric potential. Now, when you have a circuit, you can talk about the electric potential at any given point in the circuit. So you can take a point in the circuit and ask, what's the electric potential here? Okay. We'll see in a minute that electric potential is a bit like the analog of the Y value of an object when you do gravity. So you put the baseball here, what's the Y value of the baseball? Here it's a bit like the equivalent of taking a circuit and taking a point and asking what's the value of V at that point. Now, delta V, obviously from the notation, is a difference of potential between 2 points. Okay, obviously from the notation, delta something is a difference. So it's a delta V is a difference potential between 2 points in a circuit. So you take a circuit, you pick 2 points, and you can ask what's the delta V between those 2 points. Now, the key point is that delta V is what we call the voltage. In everyday life, what we call a voltage is always a difference of electric potential between 2 points. Notice the words here. The potential, electric potential, I dropped the word electric. The potential is defined at each point in the circuit. A voltage, it makes no sense to talk about a voltage at one point in the circuit because a voltage is a difference of potential between 2 points. So for a voltage, you have to pick 2 points and ask what's the difference of potential between those 2 points. And that's what we call a voltage. So we may talk about the voltage between 2 points in a circuit, or sometimes we talk about the voltage across an element, like a voltage across a battery or a resistor or something else. By across, we mean it's the difference of potential between one side of the battery, one terminal of the battery, and the other terminal of the battery. Electric potential is this analogy with gravity. Think of electric potential, like I've just mentioned, as being analogous to the height, or actually to the y value of an object in mechanics. And delta V is analogous to a difference of height. So like in mechanics, only a difference of y appeared in any physical calculation. In electricity, only a difference of potential between 2 points will enter physical calculation. You'll see examples very soon. So really, it's the delta V that is really used to calculate things that you can check on in the lab, for example. So just a quick example. Let's say you have a 12 volts battery. Okay, here you see this V stands for the units, volts. It's not an electric potential. You have a 12 volts battery. What does that mean? First of all, when we say that, 12 volts is actually a voltage. Okay, so it's a difference of electric potential across the battery. So you have your battery, and you always have a positive and negative terminal. And a battery you always replace by, in a circuit, you represent this by this drawing. So you have the positive terminal and the negative terminal. What does it mean to have a voltage of 12 volts? So a voltage is always between 2 points. So what we mean by there's a voltage of 12 volts, we mean that there's a difference of potential, okay, a voltage, a difference of potential between the 2 terminals of the battery of 12 volts. So I know that between here and here, there's a difference of 12 volts of electric potential. So it's a bit like in mechanics, you're saying you have 2 windows in a building, and there's a delta H or delta Y of 12 meters between them. Okay, so it's the difference of height. Here we have a difference of potential. Now, if I give you window 1 and window 2 have a delta H of 12 meters, you might ask, okay, but which one is the one above the other one? Window 1 or window 2? Here in a battery, batteries are the same. You have a delta V of 12 volts. Which one's at higher potential than the other one? Well, that's what the sign of the terminal tells us. The positive terminal is 12 volts above the negative terminal. Okay, so we have delta V of 12 volts, and the positive terminal is 12 volts above the negative terminal in terms of electric potential. So what I mean by this is that the electric potential here is 12 volts higher than the electric potential here. Notice I'm not telling you what's the electric potential here or here. We don't know that for now. We just know that this point is 12 volts above that point. So that's the voltage. Okay, we'll pick it up from there next time. Thank you.